This video is going to finish section 13.4, which covers motions in space, specifically velocity and acceleration. When we took notes earlier today, we looked at some background and we got into projectile motion. So we're going to today focus in this video on acceleration and a few other extra problems. So this is the third part of the chapter. Like I said, we're going to focus on acceleration. So the first half of this section, we looked at giving a position function, finding the velocity and the acceleration. Oftentimes, though, it is useful to break acceleration into two components. One is going to be in the direction of the tangent. And one in the direction of normal. The normal vector, that is. So visually, let's say that this is your space curve. Let's say we're looking at this point. We have some unit tangent vector, we have some unit normal vector, and we already talked about unit tangent vector is tangent to the curve. Unit normal vector is going to be perpendicular to it. It points inward on towards the concave part of the curve. And then let's say we have our acceleration vector. So maybe that's where our acceleration vector is. Okay, so what you're going to do, or what we're looking to do, is we're looking to break that acceleration into two parts. This being vector 1, and this being vector 2. So when you put those two vectors together, you get the acceleration vector. This first vector here that's in the direction of the tangent, that's AT. So acceleration with respect to tangent, and then likewise this will be AN. So we need to figure out how to find these. Okay, this is going to be a little bit of work. First thing that I want us to know is that I'm defining the norm of V to just be V. So I don't want to have to keep writing out the norm of V. So anytime that you see me write V, I really mean the norm of V. Okay, so then our unit tangent vector, that's going to be r prime of t over the norm of r prime of t. That's the unit tangent vector. That's the same as velocity divided by the norm of velocity. But what we just wrote above is that normal velocity we're just going to call v. So again, keeping in mind that that v is the norm of v. Okay, so what that tells us then is that the velocity vector is the same, or another way to express it is the unit tangent vector multiplied by the norm of v. Okay, so then what we want to do is we want to differentiate. When we do, on this side, we get v prime of t. This side, we're going to have to do the product rule. I'm going to differentiate that first. So I get v prime times the unit tangent vector plus v times t prime. Now, keeping in mind, though, this v, same as this v, those all represent a norm. Okay, so then this is one that we're going to have trouble with. So to get the derivative of the unit tangent vector, we're going to use curvature. Okay, curvature, if you can recall, one way to find curvature is the norm of t prime divided by the norm of r prime of t. So this is really t prime. The norm of r prime, that's the same as the norm of velocity, so that's really v. So what that tells us is that the norm of t prime is equal to the curvature times v. Okay, so at this point you're probably asking yourselves, why are we doing all this work? We're trying to figure out how to find those two components of acceleration, so how to find these two. We know how to find acceleration. All this work is going to show us how to find those two. You're not going to have to go through it every time. Don't worry about that. It's just the origination. So that's the first thing we know, or one of the things we know. Also, it might be helpful to look at the unit normal vector. Unit normal vector is the unit tangent vector divided by the unit tangent vector's norm. So what that tells us is that the unit tangent vector, the derivative, is equal to the norm of the unit tangent vector, of its derivative. Sorry, that's a derivative up there. Times the unit normal vector. But this we found up there. So that tells us that the derivative of the unit tangent vector is equal to curvature times v times big N. Okay, so how does that help us? Going back to here. Finally, going back here. Finally, we get v prime of t, which is the same as acceleration. We get that, so that v prime of t plus v, instead of that t prime, we're going to use this. So times curvature, v, and then the unit normal vector. So simplifying a little bit, we get v prime times the unit tangent vector plus curvature times v squared times the unit normal vector. Now remember again that this v really represents the norm of the velocity vector. Okay, so alternately, how we really write this. That is going to be written as AT of big T. That becomes AN of big N. Okay, so here's what this tells us. This tells us that the object is always moving according to the direction of motion which is that unit tangent vector and the direction that the curve is moving, or turning rather, which is given by that unit normal vector. So this should make sense. Okay, so now the question is, how do we calculate this A of t and this A of n? Because those two are not the most helpful ways to calculate them. While it's one way, not the most helpful. So we're going to talk next about how to calculate those. Okay, so if we start with this line again. So we get that v prime times the unit tangent vector plus curvature times v squared times the unit normal vector. Okay, so if we recall, we had the vector for velocity is equal to the norm times the unit tangent vector. So what we're going to do is we're going to multiply that into here. We're going to multiply the left side by that velocity vector, and we're going to multiply the right side by the norm of the velocity vector and the unit tangent vector. Okay, so then here's what we get. On the left side, we get the velocity vector dotted with acceleration. On the right side, once I multiply this in, I get v times v prime, and then I get unit tangent vector dotted with itself. Over here, I get curvature times velocity cubed, and then tangent vector dotted with unit normal vector. Okay, was this helpful? Well, yes, it should be. Unit tangent vector dotted with itself is 1. That's because they're both unit vectors. unit tangent vector dotted with the unit normal vector is 0. That's because they're orthogonal. So then what we get is we get v dot a is equal to v times v prime, remembering that v here means norm. What I want us to recall is that at was equal to v prime. That's from up here. At was equal to v prime. So here's what we get. At is equal to v prime. V prime from here is velocity dotted with acceleration divided by v. Now this is quick hand, so I want us to write out what that fully means. Velocity is really r prime. Acceleration is r double prime. And then v, remember, is the length of the velocity vector, in this case the length of r prime. That is how you find a of t. So all that work was to tell us that this is the formula for a of t. Now, a of t in words is called the tangential component of acceleration. Okay, so that's the tangential component of acceleration. Likewise, that a of n from up here was curvature times v squared. Okay, formula for curvature is the norm of r prime of t crossed with r double prime of t divided by the norm of r prime of t cubed. So this is all curvature, and then we have v squared. So this is the curvature, this is that v squared part. Okay, so then simplifying that, that becomes the norm of r prime of t, crossed with r double prime of t divided by the norm of r prime of t. That is our a of n. Okay, so this is called then the normal component of acceleration. So these are the two formulas you have to remember. I went through the derivation of them. I would like if you would understand them. You don't need to memorize the derivation. I'm not going to ask you about it, but I think it's good for you to see where those formulas come from. So we're going to do an example. Suppose a particle moves along C, and C is the curve given by t squared, t cubed. Part A, I want us to find the scalar tangential and normal components of A. Okay, so the reason I have scalar in parentheses is these two are normally called the scalar tangential and the scalar normal. There's also a vector tangential and vector normal. Your book doesn't differentiate between them, but I do. So you'll see that in your packet, and you'll see that likely on the test, a difference between scalar and vector, and you'll see what I mean in a minute. Okay, so here's what we know. We know that r of t is equal to t squared, t cubed. We know that r prime, which is the same as velocity, if we take the derivative, would be 1, 2t, 3t squared. If we take the second derivative, which would give us acceleration, we're going to get 0, 2, and 6t. Okay, so then if we find the scalar tangential component of acceleration, we're going to get r prime of t dotted with r double prime of t divided by the norm of r prime of t. So r prime dotted with r double prime, it's going to be 0 plus 4t plus 18t cubed divided by the norm of r prime of t, so that'll be the square root of 1 plus 4t squared plus 9t to the fourth. So that gives us a final answer of 18t cubed plus 4t divided by the square root of 1 plus 4t squared plus 9t to the fourth. Okay, so that is our scalar tangential component of acceleration. We also need to find the scalar normal component of acceleration. So that's the norm of r prime of t crossed with r double prime of t divided by the norm of r prime of t. Okay, I'm assuming that you can do this just fine. So I will tell you that r prime of t crossed with r double prime of t ends up being 6t squared, negative 6t, and 2. If you want to, you are welcome to pause the video and make sure you get the same thing, but I will tell you that that's what this vector ends up being. So our normal, our scalar normal component then, is going to be the norm of this vector. So that'll be 36t to the fourth plus 36t squared plus 4. And then the norm of r prime, we did that up here. So that is 9t to the fourth plus 4t squared plus 1. Of course, it's a good practice to see if either of those simplify or if we can divide anything out. You could divide a 4 out of the numerator. That's about it, though. So I'm just going to leave my answer like that. Okay, what I could then ask you to do is find, again, the scalar in parentheses because I use that word, your book doesn't. Tangential and normal components of acceleration at the point 1, 1, 1. So if you recall, r of t was t squared, t cubed. So if we set each of these equal to 1, we find out that at the point 1, 1, 1 is when t is 1. So what you're going to do then is that scalar tangential component that we found, you're going to plug in 1. If you trust me, you get 22 over the square root of 14. And then the normal component at 1, if you trust me, plugging 1 in here, you're going to get the square root of 76 over 14, which simplifies to 38 over 7. Okay, last question I could ask you of this type is I could tell you to find the vector tangential and normal components of acceleration at t equals 1. So the first thing we need to talk about is what do I mean by the vector components as compared to the tangential, or compared to the scalar components. Earlier in the video, we talked about we want to break down acceleration into 2 components. The first one was the tangential component. So that's the vector that we're going to multiply by the unit tangent vector. And then we have the normal component that we're going to multiply by the unit normal vector. When I say that the vector component, I mean all of this and all of this. So the AT and the AN actually multiplied by the 2 vectors then. Okay, so we have this, we have this. We need to find the unit tangent and we need to find the unit normal vectors. So unit tangent vector is r prime of t divided by the norm of r prime of t. Specifically though, we want the unit tangent vector at 1. So that's going to be r prime of 1 divided by the norm of r prime of 1. Here's r, so our r prime then was 1, 2t, 3t squared. So if I plug 1 in, I get 1, 2, 3. If I find the norm of that vector, I get the square root of 14. So then, if I want the tangential vector, which was that AT times T, so there. AT we already found up here. That's 22 over the square root of 14. I'm going to multiply that by the unit tangent vector, so that 1, 2, 3 divided by the square root of 14. That simplifies to 11 over 7, 22 over 7, and 33 over 7. So that vector is called the vector tangential component. Oh, we also need to find the normal component too. So this is the vector tangential component. Okay, we also need the vector normal component. Okay, we know from before that that's an times big N. Now, you can certainly use this. We found the scalar normal component. What you could do is you could go find the unit normal vector and multiply them. That's the definition. There's a little bit of an easier way, though. So easier way is to remember up above, we wrote that acceleration is equal to the vector tangent component, add the vector normal component. Okay, we can find that easily. We have that. This is what we're looking for. So this is what we found above. This is what we're looking for. Acceleration, you can find. We found that earlier in the problem. So if we plug in 1, we get 0, 2, 6. So then just subtract over, and you get the vector normal component to be negative 11 over 7, negative 8 over 7, and 9 over 7. Now, if you want to go and find the unit normal vector and use that, you are definitely welcome to. It just is a little bit more tedious. Okay. One more problem. We're not going to go through all of this one. We're just going to talk about it. It goes along with the problem we've been doing. What I could then have you do is find the curvature of the path. At the point 1, 1, 1. So if you recall, curvature one way in the numerator is to take the norm of r prime of t crossed with r double prime of t, and then in the denominator you have the norm of r prime of t cubed. We've found all three of those. We already know that r prime of t crossed with r double prime of t. In part A, I told you that was 6t squared, negative 6t, and 2. So what you would do then is at the point 1, 1, 1, we talked about that's when t is 1. So you would plug t equals 1 into here, find the norm. Plug t equals 1 into r prime, find the norm, etc. When you do that, you get the curvature at 1 to be 1 over 14 times the square root of the quantity, 38 over 7. So that we've already done before, that shouldn't be new. Okay. We have a few more things to talk about. Next example, the position function of a particle. Is given by r of t equals negative 5t squared, negative t, and then t squared plus t. At what time is the speed a minimum? Okay, so I want us to recall that speed is the norm of the velocity vector valued function. So first thing that we need to do is we need to find velocity. That's going to be the derivative of the position function. So we get negative 10t, negative 1, and 2t plus 1. Speed then will be the norm of that function. So we get 100t squared plus 1. Remember to square that out. You get 4t squared plus 4t plus 1. So we get 104t squared plus 4t plus 2. Okay, if we want to know when this function is at a minimum, we're going to have to take the derivative. So we're going to differentiate speed with respect to t. So we get 1/2 that 104t squared plus 4t plus 2 to the negative 1/2. And then doing the chain rule, we get 208t plus 4. Okay, minimum is going to happen when the derivative is 0 or undefined. The derivative will be undefined when this is equal to 0. So that'll be the denominator. Our derivative will be 0 when this is equal to 0. That's when the numerator would be 0. Okay, this I can tell you is never equal to 0. So you can either do the quadratic formula or you can look at a graph. You can see that that will never equal 0. This equals 0 when t is equal to negative 1 over 52. Okay, you cannot stop here. So you can't just leave an answer of t equals negative 1 over 52, because you have to prove to me that this is in fact the minimum. Now, if you remember from Calc 1 and Calc 2, proving when something's a minimum, you're going to use, in all likelihood, the first derivative test. I don't expect a sentence or anything like was expected of you in BC, but I do at least expect a number line. So we're going to have that negative 1 over 52. We're going to be substituting into the derivative. If we substitute in 0, for example, this will be positive, everything is positive. If you plug in negative 1, this will be negative, that'll still be positive, so the derivative will be negative. So this does in fact show us that we have a minimum. This shows us that our derivative is decreasing and then increasing, which gives us a minimum. So now we can say that the time is negative 1 over 52 seconds. Okay, got one more thing to talk about. This is not in your homework, but it is in the packet. And it's something you talked about in Calc BC last year. I want to talk about the difference between displacement and distance traveled. So like I said, not in your homework, but it is in your packet. Okay, so let's say that we have our position function. And let's say our initial position or our position at some point is here, and our position at another point is there. Okay, so when we're graphing this, if it's a vector valued function, that means we have vectors that are going to each of these points. So maybe this vector is r of t2, and this vector is r of t1, and then we have this vector right here that we're going to call the change in r. Okay, so then if I asked us to calculate the change in r, that would be r of t2 subtract r of t1. This is the displacement. So displacement is the difference between where you started and where you ended up. Another way to calculate this, you can integrate from t1 to t2, dr dt. So you can integrate r, or the derivative of r, with respect to t from the starting point to the ending point. Now, if I wanted distance traveled would be this part here. like how far I actually went. So to find distance traveled, which is normally called S, again, you're going to integrate from t1 to t2. This time, though, it's the norm of dr dt. Alternately, dr dt is the same as v. So we have one quick example that we're going to do, and then we will be done with notes. We are going to find the displacement and distance traveled over t is between 0 and 3 pi over 2 for r of t is equal to 1, comma, negative 3 sine of t, comma, 3 cosine of t. Okay, if we do displacement first, we're going to take r of the end point, which is 3 pi over 2, and we're going to subtract r of the initial point, which is 0. If I plug 3 pi over 2 in here, I get 1. I'm sorry, I miswrote this. This is a 1 minus 3 sine of t, so that's one component. That's really 1 minus 3 sine of t, comma, 3 cosine of t. Okay. So now if I plug in 3 pi over 2, this is going to be a negative 1, so I get 1 plus 3, which will be 4. 3 pi over 2 there is going to be 0. If I plug in 0, that'll be 0, so I get 1, and that will be 3. So our displacement is 3, negative 3. So that's one thing to notice. Our displacement here is going to be a vector. So this is the difference from where we started to where we ended up. If we do the distance traveled, we are integrating from 0 to 3 pi over 2. And it's going to be the velocity function. So you're going to have to take the derivative and then look at the norm. If I take the derivative of this, it'll be negative 3 cosine of t. So squaring that, it'll be 9 cosine squared of t. If I take the derivative here, it'll be negative 3 sine of t. So squaring that, I get 9 sine squared of t. This ends up being 9. If I take the square root, it's 3. So I get 3t from 0 to 3 pi over 2. If I plug in t is 3 pi over 2 and I plug in t is 0, I get a final answer of 9 pi over 2. So that is the distance traveled. Okay, when you guys come to class on Friday, you're going to have time to work in class, and then Monday will be a discussion day. If you have any questions from the notes, you can look in your book, or you can ask me tomorrow during class.